All right, so the relative frequency or estimated probability of an event E can be found by repeating an experiment and counting the total number of favorable outcomes. So we say the probability of an event E is equal to the frequency of the event E divided by n, where we have the frequency of the event E divided by the number of repetitions. In practice, the more times an experiment is repeated, the more accurate the estimated probability becomes. The number of times the experiment is performed is called the number of trials or the sample size. If E consists of a single outcome S, then we refer to the probability of E as the relative frequency or estimated probability of the outcome F and write P of S. The collection of estimated probabilities of all outcomes is the relative frequency distribution or the estimated probability distribution. So oftentimes this is also called the experimental probability. So if we do an experiment over and over and over and over again and make some observations, we can then use those observations to make predictions or calculate probabilities involving that event. All right. So let's take a look at the following. So example 1, 2 dice are rolled 25 times with the following outcome. Calculate the estimated probability for each sum and the frequency distribution. So earlier we talked about the sample space of rolling 2 dice when we're adding them together. So what were our possible outcomes for the sum of 2 dice? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? So those are the possible values that we can get when we add the sum of 2 dice together. So now our frequency distribution is we want to calculate, well, how many of each of these do we have? So let's make a table. So 2, 3, let's not do it that way. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All right, so let's go through and count each of these. So how many 2s do we have? Go through my list. Looks like I only have 1 2. How many 3s do I have? So I go through my list. 1, 3. Okay. Go through my list. How many 4s did I have for my sum? That's 1. I go through my list. How many 5s do I have? 1, 2, 3, 4, 5. So I go through my list. How many 6s do I have? 1, 2, 3, 4. And then I go through my list. How many 7s do I have? 1, Go through my list. How many 8s do I have? 1, 2, 3, 4. Go through my list. How many 9s do I have? 1, 2, 3. How many 10s do I have? 1, 2. How many 11s do I have? Just 1. And how many 12s did I get? 1. So those are my relative frequencies for each of these, right? Okay. So now I want to calculate the estimated probability. So our formula for our estimated probability is the frequency divided by the total number of events. So how many events did we have in this case? Well, how many experiments did we do? 25, right? We rolled the dice 25 times and collected our data. So n is 25. So then the probability of rolling a 2 is going to be 2 over 25. The probability, of rolling a 2 is 1 over 25. The probability of rolling a 3 is going to be 1 over 25. Our experimental probability of rolling a 4 is also going to be 1 over 25. The experimental probability of rolling a 5 was going to be 5 out of 25, or 1/5. Our probability of rolling a 6 is going to be 4 out of 25. The probability of rolling a 7 would be 2 out of 25. The probability of rolling an 8 would be 4 over 25. The probability of rolling a 9 would be 3 over 25. Probability of rolling a 10 would be 2 over 25. And the probability of rolling an 11 is 1 out of 25. And the probability of rolling a 12 is equal to 1 out of 25. So those would be our estimated probabilities, right? If we look at our distribution, according to this, what seems to be the most likely outcome for the sum of rolling 2 dice? Well, it would be getting a 5 appears to be the most common event. Turns out, in reality, that's not the case, but here it looks like that's going to be what it is. So then our frequency distribution would be essentially the same table that we just made, but we need to convert each of our probabilities into a decimal. So if we take 1 over 25, we get 0.04. So if we make our table, so our frequency distribution, two, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we would put in each of our decimals, so 0.04, 0.04, 0.04. For 5, 1/5 is going to be 0.2. And we have 4 over 25 is going to be 0.16. 2 over 25 is going to be 0.08. 4 out of 25 is going to be 0.16. 3 out of 25, what's that going to be? 0.12. 2 out of 25 is going to be 0.08. And then 0.04 and 0.04. And that would be our frequency distribution. So in other words, it would be our estimated probabilities, and if we converted those decimals to percents, we would have a 4% chance, a 4% chance, 4% chance, 20% chance, 16% chance, 8% chance, 16%, 12%, 8%, 4%, and 4%. So that would be our experimental frequency distribution for the sum of two dice. So here is a U-try for you guys. So the experiment is repeated 10,000 times with the following results. So calculate the estimated probabilities for each sum and the frequency distribution. All right, so let's go ahead and do this. So our n this time is we did 10,000 trials. So to calculate the probability of getting a 2, it would be 279 over 10,000. So that means we'd move our decimal to the left 4 places, so we get 0.0279. But then if we were to convert that to a percent, we'd move our decimal 2 places to the right. So that would be 2.79%. So what was the net effect of what happened here to the 279? We just moved our decimal 2 places to the left. So that'll help us. I mean, you can go through the math if you wish, but this will help us get our distribution a little bit better. So 2.79%. 3 is going to be 5.65%. 4 is going to be 8.24%. 5 is going to be 11.55%. 6 is going to be 13.94. 7 is going to be 16.77. 8 is going to be 14.43. 9 is going to be 10.72. 10 is going to get back to 8.03%. 11 is going to give us 5.14. And finally 12 gives us 2.74%. So that would be our probability distribution and the probabilities for each, right? So does this fit with our intuition when it comes to rolling some dice? Well, how often do you roll a 2 when you roll 2 dice? Is that more common than, say, rolling a 7? No. So it seems like this seems pretty accurate. We also notice the probability of rolling a 2 is 2.79. What's the probability of rolling a 12? They're pretty close to each other. Does that make sense? Well, how many ways can you roll a 2 when you roll 2 dice when you add them up? Well, what would you have to roll to get a 2? A 1 and a 1. What would you have to roll to get a 12? How many ways can each of those events happen? 1. So does it make sense that their probabilities should be similar? Sure. How many ways did we determine you could roll a 7? Well, a 4 and a 3. How about a 2 and a 5? A 1 and a 6, and in either order. So if we went back and looked at our probability or our counting chart that we had, that was that big diagonal. There's 6 ways. That was the most common number that you can get by adding 2 dice is a 7. And what's its experimental probability? And it's also the largest. So this fits with what our intuition tells us, right? It looks like getting numbers around 7 are the most likely, and then the further you get away from that, the less ways it can happen. So it becomes less probable. Okay, a couple of things we want to take note of. What happens if we add up all of these percents? So what's 2.79 plus 5.65 plus 8.24? If we add all of these up, what are we going to get? Well, let's do it. So 2.79 plus 5.65 plus 8.24 plus 11.55 plus 13.94 plus 16.77 plus 14.48 plus 10.72 plus 8.03 plus 2 more, 5.14 plus 2.74. Must have made a typo, because we should get exactly 100. Why is that? Yeah, 100%, right? Because we added up all of the possible events that could happen. I think I see what I did. I think I did an 8 there instead of a 3, because I mushed my 3 in. Okay. So this leads to the next thing on our handout, which says the following. And these are properties of relative frequency distributions, which says let S equal all the possible events in a sample space. Then let P sub Si be the relative frequency of the event Si. Then the following are true. The probability of any event in the sample space has to be between 0 and 1. Right? Because how did we form our probabilities? We took the total number of trials and we used that as the divisor for how many ways something happened. So could that ever be bigger than 1? No, the biggest it could be was 1, is if for some reason I rolled only 7s, the biggest it could be is that the numerator and denominator were the same, which is 1. Not likely, but theoretically possible. The next thing says that if we add up all of the possible probabilities of this space, it's going to equal to 1. Well, that means the probability of an event happening, of any event happening, is 1. If you run an experiment, there's going to be a result. And if you add up all the possible outcomes, it has to equal to something happening, which is 1. So then, lastly, if an event is made up of smaller events in the space, then the probability of that event occurring is the sum of the probabilities of the individuals. So if we go up and we look at our table you guys just made, let's pretend we're playing craps. So to win when you're playing craps, on your first roll, you have to roll a 7 or an 11. So what's the probability of rolling a 7 or an 11? Well, a 7 is 16.77, and what's the probability of an 11? 5.14. So the probability of a 7 or an 11 would be the sum of those two events. So 21.91. So it's just saying if you have a relative frequency distribution for events, we can add those together to find probabilities of other events that are made by combining some other things. So determine if this table can represent a relative frequency distribution. All right, so we look at this. What do we think? Could this be a relative frequency distribution? Well, let's check each of our properties. So, property 1 says that the probability of any event has to be between 0 and 1 inclusive. So what would be P of G? Well, 0.3. And what would be P of R? So this is a problem. Because what is that? That's less than 0. But P has to be greater than or equal to 0. So the answer is no, right? Because it does not satisfy property number 1. So the frequency of an event can't be negative. And if you think about it, if I told you that the frequency of me rolling a 7 on a pair of 2 dice as a sum was -5, does that even make sense? What's the least amount of times an event can happen? 0, right? That's why they have to be bigger than 0, because the worst outcome is the event never happens, right? So if I was rolling 2 dice and adding them up, it's impossible for me to get a 13. Right? And in the same way, it's impossible for me to say I rolled a 6 -2 times. It just doesn't make sense. That's why all of our probabilities have to be at least 0. That's what the first property is saying.
Positive number.
Yeah, they have to be at least 0, but less than 1. Okay. Right? So that's our first property. The second one says if we add up all of our frequencies like we did here, it has to equal 1 or 100%. And lastly, it says that we can add them together. So this one, it turns out if you add those things together, you do get 1, but that's not enough. It has to satisfy all 3. So, all right, we're going to go ahead and stop here. So these two properties, that the probability of an event has to be bigger than 0 is less than 1, and that the sum of all the probabilities have to equal 1, that was that same property, or the same thing that we were doing back in 8.2 when we did this. If we added up all of these percentages, they had to add up to 1, and the probability of any one event happening had to be less than 100% or greater than 0. So we've taken those same principles and we're going to apply them to our probability distributions. So the probability of an event E, written as P of E, is calculated by adding up the probabilities of the outcomes in E. If the probability of E equals 0, we call E an impossible event. So that was like rolling a 13 when you roll 2 dice. There's no way to add 2 dice together, numbers 1 through 6, and get the number 13. So the probability of that event would be 0, and we would say it's impossible. The empty event is always going to be impossible, because for any experiment, something will always happen. There's going to be an outcome. A probability model for a particular experiment is a probability distribution that predicts the relative frequency of each outcome if the experiment is performed a large number of times. So this is what is called the theoretical probability. So you might be asking yourself, well, why am I talking about theoretical probability in a business math class? Well, it turns out that probability comes up a lot in business and finance. So the easiest way to visualize this is, imagine you are an insurance company. What is it that they do? I give them money every month, and what do they tell me? Well, if my house burns down, what do they do? They buy me a new house, right? So that's good, but that costs them a lot of money, right? So they have to know how much to charge me. Well, how do they know? So we're going to start working with probability. So what's the probability that a house burns down? Are there other factors? These things get complicated. So coming up with good probability models or good theoretical probability models is how we work in price into a lot of different things. So this has many, many applications in finance and business besides the insurance application, because we can use those same techniques for investing and a whole bunch of other things when it comes to trading. All right, so our probability model for equally likely events is given by this formula. So in an experiment in which all outcomes are equally likely, we model the experiment by taking the probability of an event E to be the number of favorable outcomes divided by the total number of possible outcomes. That is, the number of things in the set E divided by the number of events in the sample space. Okay, so for instance, what would then be, if I had one die and I were to roll it, what are my 6 possible outcomes? 1, 2, 3, 4, 5, 6. So what would be my probability of rolling a 1? Well, how many ways can I roll a 1? 1. And how many outcomes are there in my space? 6. So I would have a 1 in 6 chance. What would be my probability of rolling a 2? Yeah, there's 1, 2, and 6 outcomes. In fact, what is it going to be for all of the numbers? 1 and 1 over 6. And if I add those up, 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6, 6 times, what do they all add up to? Which is 1. Which is exactly what we were talking about. So the idea for our first formulation of a probability model is, if events are equally likely, we can calculate probabilities by counting the number of favorable events and dividing that by the total number of outcomes. So the number of things in the event we're trying to find divided by the total number of possible outcomes. All right, so let's take a look at a couple of examples. So we were using this idea last time. In fact, we talked about the table just a second ago that you guys did when we simulated 10,000 dice rolls. So we want to use the table below. So the table below shows the sample space of rolling 2 fair dice. Use it to answer the following. So what is the probability that the sum of the dice is 7? So well, let's start with our sample space. So S is going to be this. So what is the number of things that are in S? Well, we've counted these before. It's a 6 by 6 array. So there's going to be 36 events. Okay. And now we want the probability that the sum is 7. So if we let E be the set of events where the sum is 7, well, we found those before. They're the events that are on the main diagonal, right? So how many of those are there going to be? So we have 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. So how many things are there in the event E? Well, 1, 2, 3, 4, 5, 6. right? So then the probability of rolling the sum of 7 is going to be 6 over 36, or 1 over 6. So if we were to divide that out, well, what is 1 divided by 6? So if we take 1 and divide by 6, we get 0.1666666, so 16.6% repeating. And in the experiment that we had last time, what did you guys get for your experimental probability? 16.77%. So they're not exactly the same, because one was an experiment, right? There's going to be variation as you do an experiment. But notice, by the time we got to 10,000 trials, it actually got pretty darn close to the theoretical value, which we just found was 16.6 repeating percent, right? So if you take 2 dice and you roll them, the probability that you get a sum of 7 is 1 in 6. All right, let's try our next one. Find the probability that the sum is 1. Well, we look at our event E. Is there any way to add 2 dice and get the number 1? No. So E is the empty set. So the empty set has nothing in it, so the number of things in E is going to be 0. So then the probability of E is 0 divided by 36, which is 0. So this is an impossible event. It is not possible to take 2 dice and roll them and have the sum add up to 1. All right, let's take a look at our next one. So find the probability that both dice show an odd number. So let's let the event A be the first die is odd. And let's let the event B be the second die is odd. Then E, since we want both of them, that's going to be an AND, or an intersection. So E is the intersection of the events A and the events B. Right? So we need to count the number of things in A and B. So let's count them directly, and then we'll use some formulas to help us out with that. So our event A is that the first die is odd. Well, if the first die is odd, that's going to be this row, so the first, third, and fifth rows. So that's our event A. Our event B is the second die is odd. So that's going to be the first column, the third column, and the fifth column, right? So then we have our intersection is going to be the part that's in green, right? So how many of these do we have that are in green? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So the number of events in E is 9. So we may remember the following formula. So the number of things in A union B is equal to the number of things in A plus the number of things in B minus the number of things in A intersect B. In the past, we used this formula to solve for the number of things in A union B. Well, you can use it if you know any 3 of these things. You can use it to solve for any of these numbers. So the number of things in A union B would be everything that was colored in. So it might be easier to count the things that aren't. We had 1, 2, 3, 4, 5, 6, 7, 8, 9 things not covered in. So 36 take away 9 is 27, is equal to how many things were in A? Well, A was the 3 rows of 6, so that's 18. The number of things in B was 3 columns of 6, so that's 18. And say we were trying to solve for the number of things in A union B. We would then have the formula 27 equals 36 minus the number of things in A intersect B. We minus 36, we minus 36, and we get negative 9 equals negative n A intersect B, or dividing by negative 1, we would get the number of things in A intersect B is equal to 9. So if it's easier to count other things, we don't always have to draw a picture and count directly. Because some of those things we could just figure out without having to draw a picture or do anything else, and we can use them to indirectly calculate things. So our formula here relates A union B to A intersect B to the number of things in A and B. If you know any 3 of these, you can always solve for the other. Sometimes it'll be very hard to directly calculate one of those 4 quantities, but the other ones will be easy to calculate. If that's the case, we can use that formula to help us count. Well, back to our regularly scheduled question, we want to find the probability that both dice show an odd number. Well, that can happen 9 ways. So the probability of our event is going to be 9 over 36, which would reduce to a 1 in 4 chance. So there is a 1 in 4 chance that both dice will show an odd number. All right. So the next one is for you guys. All right. So we want to find the probability that at least one of the dice show a number greater than 4. So I'm going to use our table again. Help visualize what's happening. So we want at least one of the dice to show a number greater than 4. So a number greater than 4 would be 5. So the last two rows would be where the first number is greater than 5. The last two columns, it's greater than 4. And the last two columns would be where the second die is greater than 4. So now looking at our table, if this is our event E, the number of things in our event E is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the number of things in E is 20. So then the probability of the event E is going to be 20 divided by 36, which is going to be 5 over 9. So if we roll 2 dice, the probability that at least one of them shows a number greater than 4 is 5 ninths. All right. So now, in our next example, we want to look at the following. So we have a biased coin. So normally, we would assume that a coin is fair. That means that it would be equally likely if I flipped that coin to get a head as that would be to get a tail. But in this case, that's not the case. So you have a biased coin that is twice as likely to show heads than tails when flipped. If the coin is flipped twice, we want to find the probability distribution. And B, we want to find what's the probability that you get 2 tails. So let's focus on this first part. You have a coin that is twice as likely to show heads than tails. So I'm going to let H be heads and T be tails. You could probably guess that. So then what do we know about H and T? If I wrote down the following, is this statement true? Does H equal to T? Of course not. Because what does it say? That it's twice as likely to show heads than tails. So in terms of our probability, which of those things is bigger? Is heads bigger or is tails bigger? So heads is bigger. So if heads is bigger, what must I do to make this equation true? Because right now, heads does not equal tails. So if heads is bigger, to make this equation true, I have to make the right-hand side larger. Perfect. So I'm going to multiply this side by 2 to make these two things the same. So now, they are equal, right? So the reason I point this out is it's very tempting to put the 2 on the other side. Why is that? It says that heads is twice as likely to come up than tails. But if I put the 2 on the other side, I'm already more likely to get heads. I'm just making heads even bigger, which makes the equation, not necessarily more false, but further away from being true, right? So we need to be a little bit careful. So if that's the case, what does that tell us? Well, we can combine this the fact h equals 2t with the property of probability distributions that the sum of all events must equal 1. So if I flip a coin, what are my two possible outcomes? Heads or tails. So I get the equation h plus t has to be 1. So we need to solve the following linear system of equations. That is that h is equal to 2t and h plus t is equal to 1. So in this case, it's pretty easy to do substitution, because if h is the same as 2t, we get the following equation. 2t plus t has to equal to 1, so 3t equals 1, divide by 3, divide by 3, we get t is 1/3. So if t is 1/3, then h is equal to 2 times 1/3, which is 2/3. So then it tells us that the probability of getting heads is 2/3, and the probability of getting tails is 1/3. So are heads twice as likely as tails? Yeah, is 2 times 1/3 2/3? Certainly. So indeed, heads is twice as likely as tails. Okay, so now we know what we have then. So this is our probability distribution. So our probability of getting heads is 2/3, and our probability of getting tails is 1/3. Okay, so now part B asks us, well, what's the probability of getting 2 tails? Well, let's make a tree diagram, because we're going to be doing 2 experiments in succession, right? So the first thing we're going to do is flip our coin. And what are our 2 possible outcomes? I can get a head or I can get a tail. So what's my probability of getting a head? Well, for this coin, we just discovered our heads is 2/3, right? And for this coin, what's our probability of getting tails? 1/3. Okay, so now we've got to flip our coin one more time. Well, once again, I can get a head or a tail. I can get a head or I can get a tail. And once again, to get a head is 2/3. To get a tail is 1/3. Head is 2/3. And a tail is 1/3. Well, which event did I want? I want the probability that I get 2 tails. Well, in my tree diagram, this is heads, heads. This is heads, tails. This is tails, heads. And this one down here is tails, tails. So this is the one that I want. And my probability is 1/3 times 1/3. So the probability of getting 2 tails is going to be 1/3 times 1/3, which is 1/9. So if I have an unfair coin that is twice as likely to get heads than tails, if I flip it twice, the probability that I got 2 tails is a 1 in 9 chance. Let's fill out the rest of this probability table. Well, what is my probability of getting 2 heads? It would be 2/3 times 2/3, which is going to be 4/9. The probability of getting a head and a head and then a tail is going to be 2/3 times 1/3, which is 2/9. And the probability of getting a tail and then a head is going to be 1/3 times 2/3, which is also going to be 2/9. And notice if we add those up, 4/9 plus 2/9 plus 2/9 plus 1/9 gives me 1. So if you have a biased coin that's twice as likely to get a head than a tail, if you flip it twice, the probability that you got 2 tails would be 1/9. Right? Because we had to get 2 tails brings us down here to 1/9. So notice, this bears a striking similarity to something we've done before. Back when we were counting, if I had multiple stages, how did I determine how many choices I had? It was the number of things in stage 1 times the number of choices in stage 2 times the, right, all the way out to stage n. Well, if I have an experiment that has 2 stages, what was my probability of getting a tail in the first thing? Well, what was my probability of getting a tail with this biased coin? 1/3. And I still am using the biased coin, so what's my probability of getting a tail with this coin? 1/3. 1/3 times 1/3 gives me 1/9. We're using the same counting principles here that we were using for sets. The reason that this works is because of the way that we defined probability. Probability is just counting the number of outcomes, the number of things in a set, right? Which is the same thing that we've been doing. The only difference now is, what do? We then divide by all possible outcomes, or the size of the sample space, to turn it into a probability. So we're really just counting the number of ways that something can happen. So I know at first it seems like we're doing something different, but we're not. We're just counting and then dividing by the number of possible outcomes. That's what probability is. All right. So let's let X be the event A1 is rolled, and let's let Y be any other number. So then, using the same strategy that we did above, let's start with a false statement. X is equal to Y. Is that statement true? And of course the answer is no. So which is bigger, X or Y? X is bigger. So to make that equation true, I'm going to multiply my Y and make it 10 times bigger. So that's my first equation. The second equation that we come up with needs to be that the sum of all possible events in the space is 1. So what are the possible events in our space? Well, we can roll a 1, a 2, a 3, a 4, a 5, or a 6. So we know that our first one, so we can get an x, is to roll a 1, and then all of our other events, anything but a 1 is a y. So plus y, plus y, plus y, plus y, plus y, and that has to equal to 1. So combining all of our like terms, we get x plus 5y has to be the same as 1. So using substitution that x is the same as 10y, that gives us 10y plus 5y is equal to 1, or 15y is equal to 1, divide by 15, divide by 15, so we get y is 1 over 15. Then x is 10 times 1 over 15, which is 10/15, and that would reduce to 2/3. So then our probability distribution would look like this. We have 1, 2, 3, 4, 5, and 6. And our x is 1 is going to be 2/3, and everything else is 1/15. So that's our probability distribution. So then, for part B, we were asked, well, what's the probability that a number rolled is less than 3? So we can roll a 1, roll a 2, roll a 3, roll a 4, we can roll a 5, and we can roll a 6. And our probabilities are 2/3, and then the rest are 1/15. So this one's pretty easy then. All of them are just the probabilities. 2/3, 1/15, 1/15, 1/15, 1/15, and 1/15. So what's our favorable event? We want our roll to be less than 3. Well, less than 3 is going to be a 1 or a 2. So the probability of less than 3 is going to be 2/3 plus 1/15. So 10 plus 1 over 15 is 11/15. Would be the probability of getting a 1 or a 2. So the event E that a number rolled is less than 3 can be broken down into the union of two simpler events. So let A be the event that a 1 is rolled, and let B be the event that a 2 is rolled. Then E is equal to A or B. And the number of ways that E can occur is equal to this formula that we saw before. The number of things in A plus the number of things in B minus the number of things in A and B. The key thing that we're going to have here is, since it's impossible to roll both a 1 and a 2 simultaneously. If you roll a die, you get a 1 or you get a 2. You can't roll a 1 and a 2 at the same time on one die. It's not possible, right? So that would tell us then that A intersect B is empty. And recall that when this happens, we say that the events are mutually exclusive. And then we get the following. If A and B are two events, we have that formula. And if the events are mutually exclusive, then the probability of A union B is the same as the probability of A plus the probability of B. The addition principle can be extended to more than two mutually exclusive events. So going back to the problem we just did, once we had our probability distribution, if we wanted the probability of a 1 or a 2, which is what we wanted, they're mutually exclusive, so this is the probability of 1 plus the probability of 2, which would be 2/3 plus 1/15, which is the same thing we got. So when events are mutually exclusive, their union, or their OR, is just the sum of the individual events. All right, let's keep going with that idea. So example 3 says, a survey was conducted that asked 8th grade students if they played a musical instrument, they played a team sport, and their GPA range. So below 2.0, 2.0 to 3.3, and 3.3 and above. Their responses were the following. So 42% said yes to music, 65% said yes to playing a team sport, 58% said no to music, and 35% said no to a team sport. 8% had a GPA below 2.0, 51% had a GPA between 2.0 and 3.3, and 41% had a GPA above 3.3. So now we want to ask ourselves the question, are the events playing a musical instrument and playing a team sport mutually exclusive? Well, let's find out. So what was our thing for mutually exclusive? So when we have that the intersection of the events is empty or impossible, the events are mutually exclusive. So we have our formula, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And from above, we know if this is 0, the events are mutually exclusive. So, let's see if we can figure some of these things out. So let's let A playing a musical instrument. And then let's let B play team sport. So then the probability of A union B is equal to the probability of A. And what's A? A is playing a musical instrument. So what's the probability that they would play a musical instrument? 42%. So 0.42. Plus, what's the probability that they play a sport? So 0.65 minus the probability of A and B. So then we have the probability of A or B is equal to 1.07 minus the probability of A and B. So this is problematic. Why is that? So we know that the probability of A intersect B can't be 0. Why is that? Why can't the probability of A intersect B be 0? If we go back to our definition of probability, what is the biggest a probability can ever be? 1. So and that the probability of A union B has to be less than or equal to 1. Well, we're told that the probability of A union B is equal to 1.07. Yeah, this is bigger than 1. So we know that the probability of A intersect B has to be bigger than or equal to 0.07. At least, right? Because if it's 0.07, what's the probability of A or B? 1, which is the biggest it could be. So then that means the probability of A and B would have to be at least 0.07. It's most likely larger than that, but it has to be at least that big, right? So we know that they're not mutually exclusive. So A and B are not mutually exclusive. All right. And the second part gives us one more piece of information. And it says, if it is additionally known that 20% of students play both an instrument and a team sport, what's the probability that a randomly selected student plays a team sport or plays an instrument? So in this, we're given the extra information so that tells us that the probability of A and B is equal to 20%, which is 0.2. Now we know that the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. And we have all of those values, so we have 0.42 plus 0.65 minus the 0.2 in the intersection gives us 0.84. So then this tells us that the probability of a randomly selected student playing a musical instrument or a team sport is 84%. Because if we look at it this way, this is similar to the argument we made when we were counting. The probability of A was the probability that they played a musical instrument. So 42% of them did. And 62% of them played a team sport. Well, in that, we counted the people who played both a team sport and an instrument in both of those things. All right, thank you. Yep, I did have a typo there. That should have been a 65, which will then raise that to 87. So, once again, though, we counted the people who do both sports and instruments twice. We counted them here, we counted them here, and that's why we have to subtract them off that 0.2, the people who do both, is because we don't want to count it twice. All right. All right, so complement. Let S be any sample space, and if the events A1 union A2 union AN equal S, and all of the events are mutually exclusive, so AI intersect AJ is empty for all I and J, that is that the AIs are pairwise mutually exclusive, then the sets A1 through AN form a partition of the sample space S. For any sample space S and any event A, the following hold. That the probability of anything happening in the space is 1. So the probability of the sample space is 1. The probability of the empty set is 0. And the probability of A complement is equal to 1 minus the probability of A. The last item follows from the fact that A union A complement equals S, so aka any event and its complement partition the space. So let's see. Using property 1, we have the probability of any event happening is 1. And we also know that the probability of A or A complement has to equal the probability of A plus the probability of A complement minus the probability of A and A complement. Well, a couple of things are going to happen here. So first of all, if A and A complement, so event A is something happens and event A complement is that event doesn't happen, they are always mutually exclusive. So this is 0 because they're mutually exclusive. So the probability of A union A complement is the probability of A plus the probability of A complement. But since A and A complement form a partition of the space, S is equal to A union A complement. So then we have the probability of S has to equal the probability of A union A complement, which is the probability of A plus the probability of A complement, but the probability of S is 1. So we get the equation, the probability of A plus the probability of not A has to be 1. And if you solve that equation for the probability of not A, we get exactly the formula that we had above. So the probability of A not happening is 1 minus the probability of A happening. So this formula holds for any event A. the probability of A happening plus the probability of A not happening, so the probability of A complement, has to equal 1. Because an event either happens or it doesn't. And the sum of all possible events in a probability space have to add up to 1. This is helpful in calculating certain probabilities. Sometimes an event is hard to calculate directly, but its complement may be easier to calculate. In which case, we can then use this formula to relate the two things together. All right. Let's take a look at our next example. A home loan is either current, 20 to 59 days past due, 60 to 89 days past due, 90 days or more past due, in foreclosure, or repossessed by the lender. In November 2008, the probability that a randomly selected subprime home mortgage in California was not current was 0.51 or 51%. The probability that a mortgage was not current, but neither in foreclosure nor repossessed, was 0.28. Calculate the probabilities of the following events. All right, so we've got a lot to unpack in these definitions, right? So let's see what our first piece of data tells us. So the probability in November 2008, the probability that a randomly selected subprime home mortgage in California was not current was 0.51. So let's let A be the event, the mortgage was current. So then A prime would be what? So what is the complement or the opposite of that event? So if the mortgage was current, then its complement is the mortgage is not current. And that is the complement of this event. Okay. So we can use this to help us with part A, because what does part A want? A California home mortgage was current. So we want the probability of A. Well, we don't know the probability of A, but what do we know? Yeah, so the probability of A prime, and we're told that it is 51. So 0.51. So then the probability of A is equal to 1 minus the probability of A prime. So that's going to be 1 minus 0.51, which is going to give us 0.49. So the probability that a California home mortgage was current would be 49%. And this comes from that formula. The probability of A plus the probability of A complement always has to be 1. Because it's either it is or it isn't, right? So if we can break it down into those two things, we know they're related by that formula. All right, so now let's take a look at B. So a California home mortgage was in foreclosure or repossessed. Okay. How are we going to do this one? So let's see. California home mortgage was in foreclosure or repossessed. So the probability that a mortgage was not current, but neither in foreclosure nor repossessed, was 0.28. Okay, that's going to be our key, right? So we need some events. So we know that A prime is the mortgage is not current, right? So we know the people that were current, we've already taken care of them. That's the event A. So then we have the probability that it's not current, but neither in foreclosure nor repossessed was 0.28. So how can we write an event for this? Well, what is it we're trying to find? Was not in foreclosure or repossessed. So let B be the event. So let's let B be the event that a home mortgage was in foreclosure or repossessed. And then let's let another event, C be, well, we don't want current, so 20 to 59 past due, 60 to 89, more than 90, so then what would we know about B union C? What would that have to equal? Well, that's everything but what? But A, right? It's everything that's not current, right? So B union C is everything that is not current. Well, that's exactly the same as A prime. A prime was the things that weren't current, right? From part A. And what is it that we want? We want B. So we have the following chain. The probability of A prime is equal to the probability of B union C, which is the probability of B plus the probability of C minus the probability of B and C. But the probability of B and C is going to be 0 because they're mutually exclusive. So we are trying to find that a California home mortgage was in foreclosure or repossessed. So we want B. So then our equation is the probability of A prime is equal to the probability of B plus the probability of C. So we minus the probability of C, we minus the probability of C, and we get the probability of B is equal to the probability of A prime minus the probability of C. So what was the probability of A prime? I think that's the probability of A, right? Being not current is 0.51. We're not using the answer from A. We're using what was given in the problem. And now, what is the probability of C? Well, C was not foreclosed or repossessed. Well, that's here, right? So that's going to be 0.28. So the probability then is going to be 0.51 minus 0.28. So that's going to be 0.23. So that would be our random probability of that event. So when trying to set these problems up, complements can be helpful. So some helpful advice as well. You may need to do these more than once because we picked these events and these ones worked. Was this the only possible way to define B and C? No. So if you're doing something and you start working through it and you realize it's not working, try to define some different events. You're most likely not going to pick the right events on the first try until you've practiced a little bit. It's just like anything. The more you do it, the better you will get at doing this. So don't expect to sit down and pick the right events the first time. It's probably not going to happen, right? You're going to have to practice a little bit, and then you'll get better at defining these events and making sure that they work. So things to look for are events that are mutually exclusive or complements of the event we were looking for. So that was the hint for me that helped me define the events B and C. I defined B and C in terms of another event A, but these two events were mutually exclusive, and together they made all of A prime. So that was really the key ingredient there. Because then I could use the formula. If I knew that B and C together made up A prime, I could use that because I knew the probability of A prime, right? So if you know something about an event and you can write it as the union of two mutually exclusive events, that will often be helpful. So that's a hint for helping us define what we have, is trying to break a more complicated event into mutually exclusive, simpler events, because those are the things that are easiest to do math with. All right, so let's let A be the event. So cashews or pistachios are their favorite. So then a complement would be, so So the favorite is not cashews and pistachios. Well, and that's what we want, right? Is a complement. So the probability of a complement is going to be equal to 1 minus the probability of A. So 1 minus 0.47 gives us 0.53, or a 53% chance. So we didn't need to break the event A down farther, but it is kind of interesting to think about it a little bit too in terms of a picture. So if we have cashews and we have pistachios, and it says if 47% of people ranked cashews or pistachios as their favorite, that would be, in our Venn diagram, that would be these two things, right? So then the complement would be what? So if this is A, then what would A complement be? Yeah, everything on the outside. But how does that work in terms of C and P? We didn't need it in this problem, but it can sometimes be helpful. Well, in terms of our symbols, A would be equal to C union P. What would A complement be? Well, A complement is all of the stuff that's not in C, so it's C complement, and all of the stuff that's not in P. Because if we do our picture, make it a little bigger to help illustrate. So if I make C prime yellow, so here's C, here's P. If I make C prime yellow, that's everything that's not in C, right? So that would be like all of this. So that's not C. And not P would be everything that's outside of P. But then we want the and of that. So the and is the intersection . Blue is not in P, and yellow is not in C. And we get that same green area, right? So it's kind of cool. So the complement of C union P is C complement intersect P complement. Or in other words, for any two sets, that if you have the complement of a union, it is equal to the intersection of the complements.